Okay, so I'm recording. Thanks, Adam. So today we're going to talk about a couple things. Talk about multi-threading, which is a technique you can use to get more out of any modern computer by using the multiple CPU cores that are in it. And you can use that technique in Milestone 4, but you don't have to. And then I'm going to hand things over to Dr. Tallman, who's going to talk about written document 2. Okay, so the first thing I want to talk about is just a little bit about M4 grading, because some students are curious. As I mentioned last class, it's based on your stability and your quality of results. There's no GUI component, so you can build a user interface. Might be cool for your final presentation, might help you debug your algorithm, but it's totally up to you. You're not going to demo it to your TA. It's not going to be directly marked. So to give you some idea of what quality leads to what mark, I've annotated the current leaderboards. So you can go onto the course website, click on a link, and you can see for all submissions, not just exercise runs, but submissions, what does the quality look like? You have an anonymous ID, it's posted on Piazza, how to figure out which one of these IDs is yours, but you can't tell who anybody else is. We've, on this leaderboard, put in 3 solutions that Abbott has created. So down here at the bottom part, can you see the very bottom of my screen or not, Abbott? Or is it hidden by the taskbar?
Yes, I can.
Okay, so that's good. So there's a solution called TA bad. TA bad doesn't do much optimize. Well, it doesn't do
no, I can't see the TA bad.
Okay, so let's see if I can hide this thing or not. Let's see, task. Okay.
Yeah, now I can see.
Okay, that turned off the taskbar, I guess. Nope, now it's back again. Okay. I want this taskbar to disappear. Automatically hide the taskbar. Let's do that. Okay, so now you can see TA bad down here at the bottom. Okay, yes. So TA bad really does no optimization. It just hooks everything together with the M3 pathfinding algorithm, and that'll get you some marks. You have to complete the test cases in 45 seconds, but it's not going to be a great mark, maybe 30%. TA moderate does some optimization, but it's not a really complicated algorithm, and so it's kind of related to some of the first algorithms we talked about in the lectures, and that's worth, in the C range, around 63%. TA good is using some of the more advanced algorithms we talked about, some iterative improvement and so on, and that gets up to will get you up into the A range. And already you can see that there are 5 teams that are beyond our TA good solution, some of which are a long way beyond. So you can see how much better we're basically 27% worse in average travel time on these large test cases than the best solution of the class. So there are some groups that are well beyond our TA good. For those top teams, the top 4 teams will get bonus marks. So though, assuming the program's stable, they're going to be getting a 100% on the lab and then a +1 to +4%, depending on if you're first or fourth, bonus to your overall course mark. So if they stay here and they're stable on our corner cases, this team is headed for a mark of somewhere around 130% on this milestone. So we fill a curve in between these reference points that I've just told you, 30, 63, and 82%. So if you get up at or above our TA good, you're in the A range. If you're noticeably above it, you're getting into the A+ range. The M4.h header defines what you have to do if there's no solution, and there are some cases where there are no solutions. Things are just disconnected and you can't find any path at all. We will test those. If you fail a couple of them, you'll get some penalty. If you fail a bunch of them, you'll get up to 10% penalty. So also try to be stable. Make sure you check those corner cases that we documented in the header file. Any questions on that, or is that all pretty clear? Okay, so I'm going to assume that means clear. Type into the chat if you think of a question and you wish you'd asked it a minute ago. Okay, so let's talk about multi-threading. So at the end of last lecture, I talked about why multi-threading has become increasingly important. It's basically CPUs are not getting much faster anymore. We don't know how to improve their clock frequency because we're hitting some physics limits, and we can't get very many more instructions running at once, which means they can't get more done per clock cycle, or not much more. They get a little better, but not much. But what we can do is fit more and more cores onto one chip. So you're getting the ability to run more and more things at once. That helps you run multiple programs at the same time, but for many computers, in a server, that can be quite useful. You can have many people using Google Maps at the same time and all utilizing the same server, but it's not really useful for you on your own laptop. So for those cases, multi-threading is very useful. Multi-threading basically allows one program to divide its work into separate threads, okay, so separate pieces of execution, so that you can get more done on one program when you have more than one CPU core available. And that's highly useful for you on things like laptops. So how does it work? So here's a CPU or a core. Often the terms are used somewhat interchangeably, but probably core is the term we mostly use when we have several different processors stuck on one chip. Each of those has a program counter that says, what instruction am I executing? And they have a stack pointer that points at all of their local variables that were created on the stack. So you already know that. We also have global variables, and we have variables that are created with new. So you know this from EC 244, hopefully, and from 243. When we go to a multi-threaded program, we can have more than one core working at once, and each of those cores has its own program counter. So it can be working on, it can be and generally is working on a different part of the program, and it has a different stack pointer, meaning it has its own local variables. However, they all share the same global variables, and they all share the same variables that were created with new, which are called heap variables. Okay, so we can take a program and we can put, so far you've been writing programs with just one thread. You've never thought about it. But when main is created at the very start of your program, when main starts, that is your first thread. And that's done automatically for you by the C++ runtime. But we can create more threads if we want and divide up work across them. And when you do that and you have more than one core, they can run at the same time, which is what I'm showing here. Okay, so they each get their own program counter, so they can be working on different parts of your program. And they each get their own local variables, but as I said, they share the global variables and they share the heap variables. Okay. All right, so this kind of just repeats what I said. They all get their own program counter, so they can and generally are executing a different function. They are executing a different instruction from other threads. They all have their own stack, which means they all have their own local variables, but they see the same global variables and the same variables created by new. So this allows you to very efficiently communicate between threads because they can all communicate by just using the same global variables and using the same objects that were created with new. So that's good. That's what I'm saying here. But you have to actually be careful as well. You can have threads that conflict in their reads and their writes to the same memory. So let's say I've got a global variable and I have two threads that are trying to change it at the same time. You don't know which one goes last. So you don't know what's going to happen. One of them can make an update and immediately a different thread can make a different update. You don't know what's going to happen to that global variable. So you have to be careful with these shared variables, which are your globals and your variables created with new. You can also have more threads than CPUs or cores. So it allows you to time share the CPUs, and that can be useful sometimes. In Milestone 4, we don't really want to do that. That's not really necessary. We're trying to just make a program run faster. When you're trying to make a program run faster, usually you create the number of threads equal to the number of CPU cores, because that's how many you can run at the same time. All right, so how can you do this? So you need to write some additional code to get more than one thread. You get one thread for free. Everything after that, you've got to ask for. You can do this in a few different ways. There are different APIs or different libraries that let you do this. So the one that I'm recommending you use, if you choose to use multi-threading, and again, this is completely optional. You can choose to do it for Milestone 4, but you don't have to. You can get a good solution without doing this. This is mostly if you just want to challenge yourself, want to learn something more about an important form of programming, but don't do it right away. Get a good Milestone 4 working first. So the easiest way to multi-thread a program is probably with something called OpenMP, Open Multiprocessing. This uses what are called compiler directives. So compiler directives are things like this. So hash pragma, that means this is an instruction to the compiler. Doesn't really mean anything in terms of regular C++ execution. I'm giving the compiler an instruction of how I would like it to create my program. And this particular one says, I'm a pragma for OpenMP, and I want you to run the for loop that comes right after me in parallel. So that's what that says. If your compiler doesn't support OpenMP, these pragmas will be ignored and your program will just be compiled to regular single-threaded serial code. So it'll still work. So that's nice. So anyway, that's the easiest way to make parallel programs in C++. A little harder, but giving you a little more control, is something called C++ 11 threads. So this is now part of the C++ language since a recent update that came in 2011. To use them, you include the threading standard library component, so you include thread, and then you actually create threads as objects. So here I'm saying in my main function, I said I want to create a thread. I'm going to call it my thread, and you tell it what is the start function. Okay, so the first thread in your program you get for free, and it starts executing main. Other threads with this API you create yourself, and you say what function you want them to run. Pthreads is a somewhat older library. It basically works exactly the same way as C++ 11 threads. C++ 11 threads are really calling pthreads, but the syntax is nastier. So I would say don't use that. I would recommend using this, but if you really want more control, this is also an okay choice. C++ 11 threads. Okay, so I'm only going to show you how to use OpenMP and only on some relatively simple examples, but for multi-threading milestone 4, you don't need to know a ton of OpenMP. So here's a little program that takes two vectors, A and B. Each of them have 100 elements, and they're going to be initialized to 0. And I'm going to go through all those. I'm going to go through all of those vector elements. And I'm just going to say that A is equal to whatever the A element in a certain index was plus the B element was in a certain index, okay? And then I'm going to go through and I'm going to print out what is each entry of A. So pretty simple thing. Add two vectors together, and actually there's some code in here. So let's say they're not all 0. They've been set to some values. And now I want to just add B to A, store it back into A. And I want to do that for all 100 elements, and then I want to print it out. Okay, so how would I do that with OpenMP? Okay, I've changed things a little bit here to say initialize A to 50, initialize B to 2. That just allows me to say what the output's going to be. I add in a couple pragmas. So I haven't actually changed any of the code, except I've put in pragmas to tell the compiler I'd like to run these for loops in parallel. So this says run this for loop in parallel, split it up across multiple threads if you can, and then also run this for loop in parallel. So split it up across multiple threads. So pretty easy. All right. Now these variables that are not local, they're not inside the for loop that I said I want to be parallel, are going to be shared by all threads. Okay. So all the threads that are running this first loop are going to get the same A and B variables. All the threads that are running the second loop will also get the same A and B variables. And what's going to happen is the compiler is going to create multiple threads to run this for loop. They're going to divide up the work, and then they're all going to wait here. Okay, they're going to do what's called a thread join. And then we're going to get down here. We're going to create threads again. We're going to divide up the work, and then they'll all wait until they're all done before we go any further. Again, that's called a thread join. Okay. The local variables that are declared within the for, or the block, are separate per thread. So there's an integer variable I here, that's a local variable. Every thread that's working on part of this loop will get its own copy of that I variable. Same thing here. So same thing down for the second loop. But these other variables are going to be shared by all the threads. Okay, so if I run this, I'm not going to do a demo, but I did run this before starting this lecture. This is the output I get. Okay, so the output should clearly be I initialized all 100 elements of A to 50, and I initialized all 100 elements of B to 2. So when I add them together, A should become 52 for every single value, and I should just write them out. But what I actually get is A of 0 is 52, A of 1 is 52, A of 2 is A25 is 52, A of 26 is 52, and so on. So it's garbled. So why? Anybody on the line have any ideas of why this is garbled? Let's see if I can see anybody chatting. So I'm going to give you a second to think about that. Okay, yeah, and I see a good answer from Ahmed. So Ahmed says different threads are trying to write to cout at the same time, and yeah, that's the problem. So they actually did the addition. It looks like the addition worked fine, but my output is all messed up, and it's because cout is actually a global variable, and global variables we said are shared by all the threads. Basically, everything that wasn't created inside that for loop is shared by all the threads, and that certainly includes global variables like cout. Uh, and all of the threads are just trying to write to cout at the same time, and chaos is ensuing. We're getting the first thread is writing a of 0 is 52 and a of 1 is 52. It starts writing a of 2 is 52, but in the middle of that, another thread starts writing some data. So it's kind of chaos. So we're getting output randomly interleaved. This is not good. So we need to fix it. So before we fix it, let's look at a little more detail about what OpenMP did for us. So it split the loop iterations across threads, and OpenMP on the UG machines, they have 4 CPU cores. So it's going to create 4 threads. It actually asks the operating system how many CPU cores are there, and it'll create a number of threads as appropriate, which for us is going to be 4. So thread 1 is going to get a quarter of the work. So it's going to go from 0 to 24, and this is the output routine. It's going to write out those 25 elements. Thread 2 is going to be writing out from 25 to 49 and so on. And those are threads running on actual different CPU cores, so run at the same time. But this cout is a global variable, so they're both writing to it. The order is chaotic, and we're getting chaotic output. So we need to fix it. Okay, so how do we fix it? So fix is actually pretty easy. You've learned one OpenMP pragma, which is parallel 4. Another OpenMP pragma is critical, okay? Critical means the block of code that comes after this pragma, and in this case, our block of code is just one line, because there are no braces, no loop, nothing, should only one thread at a time can execute it. So OpenMP will automatically create what are called lock variables, or mutexes, and it'll make sure that only one thread is actually executing it at the same time. So if you do that, the output will come out line by line, and it's still, the lines could still be interleaved, but each line will make sense because only one thread can get its cout at a time to print out this line. Okay, so this is like basically a speaker in the House of Commons or the Senate who is kind of policing who gets, only one person can speak at a time because that person has the gavel. Okay, so it avoids this interleaved output problem. It does slow your program down. So if we have a lot of these critical variables or critical sections, it can slow us down because only one thread can actually execute it at a time. If we do that all over our parallel 4s, we may destroy all our speed up. But that's still better than being incorrect. But you try to minimize the usage of these critical sections because only one thread can execute them at a time. So they serialize your code, they slow it down. So don't make everything critical, even though that seems like that might be an easy solution to get parallel programming going, but if you make everything critical, you're just turning parallel programming back off, so you might not have bothered. Again, I see someone is asking, what is the definition of next code block? If you want multiple lines, so I guess with this critical, it's not multiple lines running in parallel, it's actually multiple lines that only one thread could run at a time. And yeah, if you have multiple lines that you want only one thread to go into at a time, you would put curly braces around them. So you would make a block of code, and then this critical section would apply to it. For parallel 4, it applies to the next for loop. So your for loop naturally has curly braces. Okay, so I've taught you a way to multi-thread. OpenMP, as I said, if you felt like it, you could also use C++ 11 threads, but it's a little harder. Next choice you have is, okay, what should I multi-thread? So you want something that takes a lot, ideally the majority of your CPU time. Otherwise, there's no point. Okay, parallel programming is harder than serial. If you are taking some piece of code that doesn't take that long to run, there is no point to making it parallel. You're just going to cause yourself a lot of stress and work for no gain. So that's your first test. It has to take a long time. You also want the work to be independent. So you want it to be pretty obvious. How could you do this on multiple CPUs and just put the final answer together? If it's tricky to see how you would do that, then you probably do not want to parallelize it. Because again, parallel programming is harder. So if there are a lot of dependencies, you're going to need a lot of critical sections to try to organize things. Probably just, you don't want to do it. Okay, so find things that do not have many dependencies. So we've talked about some of the pieces of M4. Anybody on the line have any ideas of what might be a reasonable thing to try to multi-thread? We've got 2 tests. So what part of M4 passes these 2 tests? And there are a couple of candidates. So feel free to just chat or unmute yourself if you got an idea. And hopefully somebody's got some idea.
One student is saying iterative improvement.
Yeah, so iterative improvement is one you could do. So are you thinking you could have different iterative improvements being tried at once? So one thread is trying a certain perturbation, another thread is trying a different perturbation. Let's wait to see what the response is. Yeah, so that's a very reasonable thing to try. Any other ideas? This is your last chance to be a hero and come up with another idea. Otherwise, I'm going to tell you. Okay, so let me give you another few. So the most obvious one is actually pathfinding. So if you're writing an algorithm where you use kind of the real travel times, which will help your algorithm get better results, you need to do a lot of pathfinding before you start optimizing delivery orders. You need about, if we have n pickups and drop-offs, about 2n invocations of a multi-destination Dijkstra algorithm. They're all doing independent work. They're all starting from a different source and finding the travel time, shortest travel time to all of the interesting destinations. So those are totally independent. And it takes a reasonable amount of CPU time that you need to finish before you can go on to optimizing the delivery order. So that's a pretty reasonable thing to make parallel. Another one would be multi-start of your order optimization algorithm. Okay, so we said that you can take any algorithm and just try it with different starting points, and you'll tend to get somewhat better results. So those are independent because you're just trying to start from different starting points, and you're not trying to share any information. And they could take a long time if your algorithms are complicated. So that's actually another thing that's pretty easy to see how you can make it parallel. And this is the one that was suggested by Ilgiu, which is multiple perturbations to the delivery order at once. So this is doable. It's actually harder if you're storing one best solution as you make different perturbations. That best solution would be a critical section because you'd only want one of your perturbation threads to update it at a time. And that might hurt your performance. You could say, well, you're going to try 1,000 perturbations in each thread and they'll keep their own best solution. And only after they've each done 1,000 will they try to update the overall best solution. That might minimize the amount of time you spend in that critical section, which could get you better parallel speedups. So that's reasonable too. But basically, this one's a little harder. Parallel programming is surprisingly difficult when you start getting dependencies. So it's harder to debug. When you bring up a debugger, you'll actually see instead of your program is on this line, you'll see you have 4 threads and they're on these 4 lines. So you can imagine that's actually harder to think about. And they can all be updating variables. So multiple perturbations, doable, a little more tricky. So I see, actually,
yeah.
Sorry, go ahead. I see there's a question of what's the difference between core and thread. So let me just quickly answer that. Core is a hardware unit. So on pretty much any modern CPU that you would get in a laptop or even like a decent cell phone nowadays, the processor chip has multiple cores in it. And each core is what would once have been called a CPU. They're basically a bunch of independent processing elements that have been put on one computer chip and collaborate. So it's a hardware unit. So you can run multiple programs or you can run multiple threads at once. Thread is a programming construct. It means in one program, I have multiple things that can be done at once. And those threads each have their own program counter, so they can be executing a different instruction. And they could be run one after the other on the same core. So that's time sharing a core. Or nowadays, when we have multiple cores on a single chip, they could all be running at once on different cores. And that's the case we're more interested in because we want to get things done faster. Does that make sense? So core is a hardware unit. Thread is really a software idea of how many threads of execution you divided a program into. Abid, did you have something to add to that?
No, I was just letting you know about the question.
Okay, thanks. Okay, so let me do a quick poll. So how much speed up can I get? So let's say I've written my milestone 4 and I spend 40% of my time, well, I spend 60% of my time doing pathfinding. So I kind of do that at the start. I figure out all these travel routes between all the destinations, all the best paths. And then I spend 40% of my time trying to reorder my delivery order to get a better solution. So if I look at this, I go, well, pathfinding takes most of my time. So I should always work on the biggest CPU time first, if I can. So let's make that parallel. Okay, so how much speed up could I possibly get? Okay, so I'm actually going to try launching a poll here. Let's see. All right. Abid, do you see a poll?
Yes.
All right, so let's see. I'm going to, let me define what speed up is. Whoops, I don't want to do that. I just voted, I think. Okay, fine. Let me try, okay, so let's see if I can leave that alive. And okay, so let me move this poll over a bit. So the definition of speed up, because you need to know this in order to compute the maximum speed up we could get. So speed up is basically just the opposite of time. So you take how long did it take to run a program if you ran it on one core, so you ran it serially, and you divide it by how long it took if you ran it on all the cores. So you ran it with as much parallelism as you coded. Okay, so a high number is good, it means you got a lot of speed up and ran a lot faster. A low number is bad, it means you wasted your time doing any parallel programming. And on the CPUs we're using, you have 4 cores, okay? So to first order, if you make something parallel and you don't have any critical sections and so on, you know, if I have 4 cores, it'll run 4 times faster, right? Because I have 4 threads sharing the work. But for the case I've given you, I'm only going to make the pathfinding parallel. I don't know how to make my path order parallel, or I'm running out of time, I can't write the code. So what's going to be the impact on the overall speed up of the whole application, the whole milestone 4? So let me give you another few seconds to think about that. You got 4 choices here. Okay, so I'm going to give you another 15 seconds or so. So if you're still thinking about it, type it into your calculator quickly, and I'm going to end the polling. All right, so let's end the polling, see what people thought. And so you can see the number 1 answer was 1.8. And that's actually the right answer. A reasonable number of people thought there'd be a 2x speed up, and quite a few thought there'd be a 4x speed up. Okay, so on the pathfinding, you could get a 4x speed up. Pathfinding actually there's not a lot of dependencies, so you should get around 4x. But that's only 60% of your runtime. And the path order, I'm not changing at all. So let's see how we combine those 2 things together. And let's see. Okay, so let's just bring that back up. So pathfinding time drops by at most 4. If we have done a good job, don't have many critical sections, it's 4 times faster. So we compute our total time as 0.4 of our time is path order. That hasn't changed. 0.6 of our time was pathfinding, and we divide that by 4 now. So we add it all up. The total time is 55% of what it was in serial. And the speed up is just the inverse of that. So the speed up is 1.8x. So that's a pretty reasonable speed up. But often people are disappointed when they write parallel code of why I did all this work to write parallel code and I have 4 CPUs, why isn't it 4x faster? And there are a bunch of reasons, but the biggest reason is this, that you've probably still got a bunch of serial code and that limits your speed up. So this is such an important result that it's called Amdahl's law after Gene Amdahl, one of the pioneers in the mainframe industry. It's why you also always want to get a good algorithm before you try to make things parallel. You can get more gains usually by using a better algorithm than you can by making things parallel. Okay, so let me talk about something that you got to be careful of. So when we looked at our pathfinding algorithm, we had to store these reaching edges. So for every node, we needed to store how did I get here, so that once we found a destination, we could do this backtrace routine and we could find what was the path. So we needed some way, let's say for every node ID, so a vector of integers, we have, we have a vector and we can access it by node ID number, and we can ask what's the reaching edge that was used to get to you. And we did that in our pathfinding algorithm. And now we basically take our pathfinding algorithm, which is going to go through all of our deliveries, and so every start location, and it's going to basically say invoke a multi-destination Dijkstra path search, starting at that location and going to all the other deliveries. Okay, and this path search algorithm, this multi-dest Dijkstra, is using this reaching edge. Okay, that's how it's figuring out when it gets to the destinations, how did I get here? Okay, so that's a problem because this is a global variable. So we would have 4 different path searches happening at the same time. They would all be using the same reaching edge, but setting different entries in the vector to different values and basically causing chaos. So the easy way to fix that is to make this local. Do not declare this as a global variable anymore. You need to put it inside this for loop and declare it locally. And then every one of the 4 threads would get its own copy of that. So that's generally your major challenge when you're taking an algorithm like this Pathfinder, where there aren't a lot of dependencies in the algorithm. You might have created dependencies by using global variables, and you need to get rid of those. It's okay to have multiple things read a global variable that they never change. So they may be able to read a graph of what's connected to what, but it's not okay to have multiple threads changing global variables at the same time. So this would have to be made local or it'll crash. Okay? You could have made this critical. There are other ways you could do this, but they're not good ideas. Okay, so you should make this one local. All right, so keep it simple. So as I said before a couple of times, you do not need to multi-thread to get a good milestone 4 implementation. This is really just a useful programming concept we want to expose you to. So get a good serial implementation before you try to multi-thread. It is much harder to write and debug multi-threaded code, so it is not the first thing you should do. And if you're busy and don't want to try it, that's totally fine. And if you want to go further, here are a couple of resources: an OpenMP tutorial and how to debug threads with GDB. It is harder to debug, so you have to kind of steel yourself for that. If you want to learn more about this, in ECE 454, Computer Systems Programming, you learn how to make programs go fast. You do things like profile them to see where is your time going. So you did some of that in this course. You do more in ECE 454. How do you write code that will be fast when it goes through a compiler? So you learn some more about what compilers do and what code structures tend to be faster and slower, what things tend to fit in caches well versus not. And you'd learn how to write more parallel code. If you want to learn about how do CPUs make programs run fast, you can take ECE 552, which goes into some of the, how do we make multiple cores work well together on a single CPU. I told you that you can run on a modern CPU core, it's running about 30 instructions at once, but it provides the illusion to the programmer that's running one at once. That's actually very complicated. This course would tell you how does that work? How do you really make CPUs do that? And that is all I have. So with that, I'm going to hand it over to Dr. Tallman. While he's taking over, if there are any questions, type them in or ask. Let's see. Someone is asking when he tries threading, the maximum CPU percentage is 400%. Is hyperthreading not available or it's not reported? Okay, so great question. Okay, CPU percentage 400% means you're using 4 CPUs completely. The CPUs in the undergraduate labs are 4-core machines. Okay, so there are 4 cores. Each of them is called two-way hyper-threaded. What that means is they can actually run 2 threads at once, because each CPU core has multiple execution units. When they run 2 threads at once, they don't actually, they slow down some. Each thread might run at 75% of the speed because there's some contention between them, but you might get 1.5x the throughput. That is turned off on the undergraduate workstations, so you can only get 4 threads to run at once because hyperthreading is turned off. Why is hyperthreading turned off? It's turned off because it was found to be a security risk by Intel. If you've been following Spectre and Meltdown, if you just do a search for that, you'll find that there are various weaknesses that people have found recently when CPUs are running many instructions at once, and particularly if those instructions come from more than one thread. People have found, they've been able to show security vulnerabilities where you could try to steal information that way. No one has actually managed to create an application that has shown they can do this in any practical way, but they've been able to show that in sort of constructed examples, they can leak information. Intel has gotten nervous. They've released various patches and they've turned this off for now. I asked one of my former grad students who's actually working on designing the next generation x86 processor, is hyperthreading coming back in a future processor? And he said, yes, they will bring it back. I asked, will it be safe? And he said, it will not be 100% safe. He said 100% safety is not possible. So it'll be safer, but not perfectly safe. People who are super worried about it will continue to turn it off. People who are less worried will turn it on. But on the undergraduate machines, last year, hyperthreading was on. This year, because of those security vulnerabilities being found, it's now turned off at Intel's recommendation. So great question. Anyway, so let me hand it on to Ken before I take too much more of his time.
Great, thanks very much, Vaughn. So I'll just switch over here to my slides and get this up. So Vaughn, can you see my slides on the screen?
Yep, I can see them, Ken. Thanks.
Okay, good. Welcome, everyone. Looks like we've got about 12 minutes left. So as Professor Betts said, I'll spend some time today talking about WD2, the lessons learned assignment, and I'll finish off with any bits that I've got left tomorrow, and then start to focus on OP2. And I know that for most of you, you're working on milestone 4, lots of other things, so these assignments are a little bit on the horizon, but this is hopefully a good time to get you started in on your thinking. This is a quote that I like a lot. Some of you may know Ernest Hemingway, the great American writer from the 1950s, 60s. One of the great things about Hemingway is that he had a lot of advice for writers. And this was advice that he wrote when he was very young, back in 1924. And he was writing here about how to overcome writer's block. That when you're sitting down and you don't know what to say, the words won't come, just to write one true sentence, right? The truest sentence that you know. And I was kind of thinking how appropriate this is for WD2, where really the task with the lessons learned is to write something that's really true, right? Try to get to something that's really meaningful for you. And so I had this kind of quote come to mind when I was thinking about the assignment. Getting help with WD2. Now, I believe these dedicated sessions are already set up, although I heard from someone on Piazza that they tried to get in and book one of these appointments and they weren't yet available. So I'm looking into that. If there is any delay with that, I'll certainly try to take care of that.
So Ken, there's a student who's posted on the chat that they are now set up.
Okay, excellent. Thanks very much. Good. Let me get the chat up here. Chat. Okay, good. I'm seeing the chat now as well. Good. Thanks for that. I'm not advancing. And as you know, the assignment due date now is extended to April 9 on this assignment, so that gives you a little bit of extra time. And the assignment itself is very compact. The wording is, as you see, it's very concise. You know, I like this quotation from John Powell: "The only real mistake is the one from which we learn nothing." And I think maybe one of the things you've experienced during this course working on a team is that you're continually checking in with each other, certainly on a weekly basis, about, you know, what's working, what's going ahead, where are the challenges. We do that as well on the instructional side, that we meet each week, and we're trying to learn about how to be more effective, how to do things a little more efficiently. So this is kind of an ongoing process, I think for all of us. And so for this particular assignment, we're asking you to take 2 lessons, one from the technical side of the course and one from the communication side. And really the main objective here is that we're looking for insights that you can carry forward to future projects. You know, if you identify that something maybe didn't work too well in the course here, if you can't really project it into the future and see how you could maybe overcome the obstacle, how you could, you know, overcome the problem, that there won't be much value. So for you yourself, you might be wanting to really look at how you could carry forward these insights to future projects. And I guess by that we mean that that you kind of generalize the lesson that you've learned. And maybe I could give a quick example here. I was talking with the team that I meet with weekly earlier today, and we were talking about Dijkstra's algorithm. And so we were thinking, well, as a lesson learned, okay, so you learned maybe how to work with this algorithm. But for the future, what is really the value in this? What was the value in the way that you learned to develop this, the knowledge here? And one student was saying, well, the main lesson was that she learned how to, start with something that's simple and then incrementally build it up to something more complex. And that as an approach, it's something that Professor Betts advocated and something that she tried and worked well. So then the general message there is that she learned how, in the process of working with this algorithm, to start with something simple and move step by step. So that seemed to me to be kind of a good example of how you might take a lesson in the course and apply it in a broad way to the future. A few students have asked about, well, what's technical and what's communication? And that's a good question. Sometimes it's hard to see the difference. Could be that in some instances they're integrated. And I think probably in this course, it's one thing that Professor Betts and I have sort of promoted is that in the design process, in this case, software design, that communication is part of that process. So it could be that, for instance, a team lesson might come on the technical side, it might come on the communication side. So, we see that there's a certain amount of interplay between these two areas. And, I think if you're concerned about this, certainly speak with your CI as you're developing your ideas. The rubric, I just point you here to, again, this plan for the future. You want a concrete plan that has appropriate breadth to apply to future projects. So again, if it's learning Dijkstra's algorithm, it's not that then in a job in the future you'll be able to use Dijkstra's algorithm. It's that you'll have a better understanding of the process of how to approach an algorithm like this, to start with the simple, move forward incrementally, or something of that nature. That the quality of the writing is concise. A few of you have asked whether you need an introduction. And you certainly could have a brief introduction. The word count is very limited here. So it could be that you start right in with the first lesson. It could be that you have a short framing statement. That's really up to you. So where to find the lessons? You know, it's something that you want to think about yourself, and it may be that there's a few things that pop to mind immediately that you want to use. It may be worth spending a bit of time thinking a little bit more deeply. One of the things that I brought to the students last year for this was you've probably seen this poster of the graduate attributes. And for those of you who don't know, these are developed in accordance with the accreditation board's requirements that learning assessments with respect to each of the 12 graduate attributes by the accreditation board be considered, and that if we as an institution cannot show that students have become trained in these areas, the CEAB will not give accreditation to the university. So the 12 of them here cover a lot of range. I've pointed to a few that might be relevant to the work that you've done here in ECE 297. You've certainly worked on design. You've worked on some problem analysis. You've done individual and team work. You've worked on communication skills, on professionalism. You may have done some work with ethics and equity in your teamwork, perhaps. Certainly project management. And the last of the 12 graduate attributes, lifelong learning, which is described as in the attributes as independently the ability to summarize, analyze, synthesize, and evaluate information from a wide variety of sources. So being able to take in information, synthesize it yourself, and evaluate it, and to develop a strategy to identify where there may be gaps, perhaps in your own knowledge. And so this may be an area that this attribute that might be worth considering as you think about your WD2 document. You may also want to consider the made-to-stick principles. How could you make use of those perhaps in the lessons learned? Could have to do with making things concrete, making things credible, maybe using story, using emotion, a number of things that you may be able to make use of there. So I see that we're already just coming in at 6 p.m. already. So I'm going to continue tomorrow with a few examples of student work from the past 2 years. You can view a few short samples and we can evaluate the effectiveness of those. And then I'll move on to OP2 in more detail for the main part of the presentation tomorrow. So any quick questions? I'm looking at the chats here. Anything that you want to ask me about WD2? Okay, I'm not seeing anything right now. So good. So we'll check in tomorrow at 5 p.m. and I hope you all have a great evening, and see you tomorrow.
And maybe I'll just jump in for a second.
Yeah.
In the chat, there was a bunch of discussion going on about, you know, what's more important, the circumstances or the lesson going forward.
Okay, I didn't.
Would a Git conflict be a good? Is there some answers on the chat? But I think for the people watching the recording, it might be useful to just discuss that as well. So I guess a few interesting questions are: what's more important, the lesson circumstances, or what you, the lesson you draw from it for the future? And already there's an answer about both being important, but maybe you want to expand on that. And there are a couple of quite specific questions on would this be a good lesson? Would that be a good lesson?
Okay, let me just get a look at these. So personal issues, disruption, unable to connect, they count for the communication side. Yeah, sure. I think that these would be certainly valid considerations on the communication side, and may be very relevant to many of you due to the kinds of challenges that we've recently had to deal with. So certainly I would think that would be very relevant. And then this is a good question from Alex. What's more important, describing the event or describing its application? And I would say that probably for yourself and for the reader, that seeing how you can apply it and generalize it is going to be perhaps most valuable to you. I can see that Cheryl, our CI, is chiming in that both are equally important, and I think that's true. I think that often the more difficult thing is to be able to apply it and generalize it for future use. So that may be the most challenging part. Do we have to put appendices? No, we don't. We don't need any appendices for this assignment. So just I think it's 450 to 500 words is what we're after there. So yeah, so those are all good questions, and tomorrow certainly we'll be able to field more questions on this. Good. Okay. So I don't see any more questions coming in. Did I miss some?
I think that was mostly it. There was some discussion on chat of, would a Git conflict be a good thing to discuss? I think that seems like a reasonable way to do it.
Absolutely. And it's sort of one of those areas where the technical and the communication side of the course come together. And I think many students in the past have seen that when they're discussing communication, they're also, in some respects, discussing some of the technical parts of the course. So the two are often closely integrated. And as I said, I'll just close just repeating the point that the process that most of us work through on a weekly basis is to look at what we've done as a team and to see where things have worked well and try and repeat those, build on those, and then to look at where there were challenges and look how we might best overcome those. And so that's kind of an ongoing process. And so this assignment that we're giving to you at the end of the term is hopefully something you've been really kind of working on all term long. So it'll seem pretty natural to find something to fit in here. So good. So thank you, and we'll see you tomorrow.
Sounds good.